Solving LPP by analytical methods. Part 2. Systematic trial and error method. The arbitrary trial and error method is not dependable analytical method as a huge number of trials are required and there are no logical link in the trials. Systematic trial and error method aims at minimizing number of trials and ensuring better outcomes in succeeding trials until the optimal solution is obtained. Let us consider the same LPP dealt in the earlier video. This is its general form and we convert it to standard form by addition of the slack variables as seen earlier. Now, in case of a systematic trial and error method, we have to begin with initial feasible program and then we will go on improving the program until the optimal solution is reached. So the basic variables from these two equations are identified. The basic variable is one which has positive 1 coefficient in one of the equation and it is not present in the other equation. So we have S1 and S2 as the basic variables in these two equations. We can write an expression for S1 by using equation A. Similarly, an expression can be written for S2 by using this particular equation B. Now these are written and we will get the initial feasible program. We write S1 is equal to 6 minus twice y minus y from A and we will call this as C. We will get S2 is equal to 8 minus x minus 3y from B and we are calling it as D. Now equating x and y to 0, we can get values for S1 and S2 and the Z for this particular initial program is equal to 0. Now we have to decide whether the improvement in the program is possible. We can take help of the objective function. I am going to call it as a Z1 for the initial program, which is similar as one that we had written earlier for the standard form. Then we can conclude that if 1 unit of x is brought in the program, there will be improvement by 4 units. Similar is the case of y, wherein the improvement will be positive 3 if you bring 1 unit of y in your program. Now obviously we will select x because it has a large potential for improvement. Then the x is called as incoming variable. Now once x has to enter in the program, one out of these two members, that is S1 and S2, they have to go out of the program because we know two equations can be solved only for two variables. So which one has to go out of the program, S1 or S2, can be worked out by finding maximum value of x possible by the two constants. If all variables except x are set to 0, from C we will get x is equal to 6 by 2, whereas from D we will get x is equal to 8 by 1. The maximum quantity of x will be equal to 3 because if you consider it as equal to 8, say it will not be feasible because the constant C doesn't allow to have the quantity of x more than 3. Therefore, the constant C is called as a limiting constraint. So from C, we get x is equal to, just by rearranging the terms, x is equal to 3 minus 0.5y minus 0.5s1. Let us call it as E. Then using E, we can revise the expression for S2 and it will become S2 is equal to 5 minus 2.5y plus 0.5 S1. Let us call it as F. Now using again the expression for x from E, so we can modify the objective functions. I will call it as Z2. And I have put for x from the equation E. I had eliminated this 0s1 plus 0s2 because they don't have any addition in the objective function, as the objective coefficients are 0, 0. So I get Z2 is equal to 12 plus 5 minus 2 times S1. Now again, if I look towards this particular objective function, say if we are able to bring 1 unit of y in the program, the value of z is likely to get increased by 1 unit. So we will try to bring as much as y possible in the next program, and in the next program the y is going to be the incoming variable, and when y is to be brought, so what is to be done? So let us see. Now the first revised program that we had seen is we will propose x equal to 3, then y is equal to 0, s2 is equal to 5 and s1 is equal to 0. The value of z found out was 12. Now as we have seen, the incoming variable is y. Again, to determine outgoing variable, we have to determine what we call as a limiting constraint. For that purpose, all variables except y are set to 0. Then from E, I will get y is equal to 3 upon 0.5, that is equal to 6. Whereas from F, I will get y is equal to 5 upon 2.5, that is equal to 2. The maximum quantity of y that is possible is 2. It is because, say, the constraint F is not allowing us to have more quantity of y than 4. So the F is going to be the limiting constraint. By using the limiting constraint, that is F, we get y is equal to 2 plus 0.2 S1 minus 0.4 S2. We will call it as G. So from again the E, equation E, by substituting for y, we will get x is equal to 2 minus 0.6 S1 plus 0.2 S2. Let us call it as H. Now, again we can modify Z3 by putting the value of y from G, that is 12 plus, this is y, minus 2 times S2. On simplification, we get Z3 is equal to 14 minus 1.8 S1 minus 0.4 S2. So we get the second revised program. In the second revised program, say we will have y is equal to 2 minus 0.2 S1 minus 0.4 S2, that is the earlier expression G. Similarly, the expression that we had obtained for x, H, and the Z is getting modified to 14 minus 1.8 S1 minus 0.4 S2. Now if we look at the objective function, say we don't have positive coefficient to any of the variable. Therefore, the further improvement is not possible. If you try to bring S1 in your program, the 1 unit of S1, then in that case the Z will be getting reduced by 1.8. Similar is the case of S2. And therefore, say here we can conclude that we have reached to the optimal solution and no further improvement is possible. So you might have noted, say within, say 3 trials only, say we are able to reach to the optimal solution. In contrast with the arbitrary trial and error method, say where we were required to consider 6 cases. Thank you for listening.